Go with Unit 4.05. We're going to be solving radical equations by hand. And in order to get us to the point where we need to solve, I want us to actually start by looking back at the problem that we did today in class that will kind of motivate why we might want to solve radical equations. All right, so here's the question that we worked on today. If you and your team did not completely finish, what you're going to want to do is go ahead and actually complete this on your own. Feel free to collaborate with one of your teammates or someone else and post questions that you have on the comment list, and someone might be able to help you out. And I will also, in about 5 seconds, go over some of the key pieces, but make sure you've given it, you've solved it yourself first. All right, so in thinking about just beginning by sketching a graph of velocity, as r is increasing, and I know this is a square root function, so before I even go about creating a table, if that's my plan, I just can start thinking about, okay, well, there's no, I'm not adding anything on, so I know that my y-intercept's going to be at 0, and I know it's going to look something like that. I know I'm multiplying by something, and in fact, I can split this up so that I can rewrite it as the square root of 2.7 times the square root of r, and that is pretty much equal to, we can estimate by saying 1.6 times the square root of r. So I can see that I'm multiplying the square root parent function by 1.6, so it's going to be pretty close to the regular square root function. And then I can go ahead and then start plotting some points, and I'll do this rather quickly. And I just chose some values that I could easily plug into my calculator. You could also do this kind of in your head by using square roots or r values that are easy to square root. So you could use, for example, 49 and think about, okay, 49 is, square root of 49 is 7. 7 times 1.6, and you plug that in your calculator and also use that. And so rough sketch of my function looks something like that. Then go ahead and figure out, you'd plug in 900 into your function to figure out what your velocity would be if you had a 900-foot radius. Thinking about the change between 40 and 50 feet and the change between 70 and 80 feet. And here we're going to start to look at, well, as my radius is increasing, is my function changing more or starting to change less? And the shallower that it gets, the less it's changing. And we can see that as I'm moving on, and if I break this up into little intervals, think about this interval here, and then think about going there, and then from there to there, you'll notice it's getting more and more shallow. And so I'd expect the change in maximum speed between 40 and 50 to be greater than the change in maximum speed between 70 and 80 because the function is kind of getting shallower and getting flatter. The y-intercept is, of course, at 0, and so this, is pretty easy to think about. This means that my r value is 0. So if there's no curvature in the road, your velocity that you could safely travel at it would be 0. And what that really means is that you're taking such a sharp turn. Let me see if I can sort of visualize it. You're coming up and you're going to take such a sharp turn that it doesn't even have a radius. It's almost as if you're immediately making a 180-degree turn without there being any radius whatsoever. And that's going to be pretty much impossible. So it makes sense that the safe speed would be 0. And then finally, the last piece, but I think the most important piece, is to think about what would happen if instead of saying that this were 1.6 times the square root of r, if I said, let me use the function, do it in a different color here, if I were to use the function v equals 1.6 r. And we could start to graph this out, and I'm going to do so in just a second, but what you will notice is this is a linear function. This is going to be a straight line with a slope of 1.6. And so you might guess what this will look like, and I'm going to just plot a few points now so that we can get a better idea. And so there you have it, and what you'll realize is pretty obviously that this straight line is going to continue changing by the same amount over time. Whereas my square root function is getting shallower and shallower over time, and so it's not changing by as much, right? And That is an important feature of square root functions. So it'd be a good idea to go ahead and sort of synthesize that in your notes. And what I'd like you to do is actually write a couple of sentences in your notes for yourself about the difference between a linear function and a square root function. So go ahead and pause the video, write that down, and I'm going to talk about what you should be saying to yourself. The basic idea is that this linear function, 1.6r, is always going to be increasing by the same amount. It's got a constant slope, whereas my square root function is actually going to be increasing by less and less over time, and it does not have a constant slope. Okay? And we'll continue to talk about this and understand this better as we look at more examples, but that is a good distinction to make. All right, so let's continue now. Say that I have this formula, and the situation arises where I want to create a turn where it is safe, I can safely travel at 65 miles per hour. Okay? Maybe I'm designing a highway, and I need to know what the radius is going to be if I want to make sure that people can safely turn on the highway. So I want you to pause the video now, and I want you to try and figure this out on your own. Okay? So I'm sure you had some good ideas, but the basic gist of it is we have an equation that relates the two variables, and we know the value of v. We know that we want the maximum safe speed to be 65 miles per hour, and we're looking for the radius. So one idea, and this is the correct move, would be to say let's plug in these values that we know into our equation. So we're solving the equation 65 equal to square root of 2.7 times r. I want you to go ahead and try solving this on your own. And there's a couple of different ways we can think about it, and I'm going to go over in one direction and sort of explain another way of thinking about it, so hopefully it makes a lot of sense. But try it on your own first, try and solve for the r value and see if that makes sense, right? Go back to your graph, look at it, decide whether that makes sense, and then we will kind of dive in. So the first way that I'm going to talk about this is just think about what you're trying to do. We want to solve for r, and currently we have a situation where we're taking the square root of something times r. So it makes sense that we're going to have to sort of, in a way, get rid of this square root, or not have the square root of r anymore. And the first way to think about it is to say, okay, well, when I'm taking the square root of something, what I'm really doing is raising it to the 1/2 power. Okay? So I have, my equation now looks like this. And at this point, you will remember, okay, I don't want r to the 1/2, I want r to the 1. So what will I have to do so that I have r to the 1 instead of r to the 1/2? Well, we know that when we raise exponents to another exponent, we multiply them. So if we raise 1/2 to the second power, we'll end up multiplying 1/2 times 2, and that'll give us 1. And so I do that to the other side as well, 65 squared. And I need to do that because I can't multiply, I can't raise one side to the second power and not do that to the other, of course. And so now I'm in a situation where on the right side of my equation, I'm left with 2.7 times r. And on the left side, I have 4,225. And at this point, very simple. We just divide on both sides by 2.7, and I find that the r value that I was looking for is just a little over 15,064, or to be a little more precise, 1,564.8, and that is, of course, in feet. Okay, so if that made sense and you understand how that works, that's great. I want to briefly go over kind of the intuition behind this and why this works. And so to do that, I want you to just think to yourself, okay, let's say that you have the square root of 4. Okay? Well, the square root of 4 is a number that you can multiply by itself to get 4. So if you were to multiply the square root of 4 by the square root of 4, well, what would you get back? You'd have to get back 4, right? Because this is the number that you multiply by itself to get 4, and this is the same exact thing. So when you multiply it by itself, you're obviously going to get 4, and that should make sense. Square root of 4 is 2 times 2, which is 4. Right? And you can test that out with anything, and it will work. And so when I go up here and I think about this, I'm thinking about the same thing, right? If I multiply the square root of something by that square root of the same thing, I'm just going to get back out whatever it was that I'm taking the square root of. And what does it mean to multiply something by itself? Well, that just means to square it. So really what I'm doing here is taking the square root of 4 and squaring it. Okay? And so if you go back to our situation up here, what I was really saying is, okay, let's multiply on the right side by the same thing, 2.7 times r. And when you do that, you've got to multiply on the left side by the same thing, by square root of 2.7r. But what is the square root of 2.7 times r? Well, for our purposes, imagine that this were blocked out. Remember that what we started with is that the square root of 2.7 times r is 65. So that's the same as multiplying by 65, so I'm going to multiply on the left by 65. Now, of course, 65 times 65 is 65 squared, and on the right, what I'm really saying is that I have this value here squared, right? Which is what I have here, 2.7r to the 1/2, which is the same as taking the square root and then squaring it. Okay, so that's kind of the intuition behind it and why it works. And we just sort of will go on, kind of always thinking about, well, I'm raising it to the 1/2, so I can then raise it to the exponent of 2, and I'll end up with an exponent of 1. But that's the intuition behind it. So here we're going to try some, and I want you to try these on your own. And I want you to think carefully about whether the answer that you find is actually possible. Okay, so make sure that you're always considering whether or not there is actually a solution. Don't just assume that there's a solution to these equations. So go ahead and try solving them out. Remember how to deal with the square root like we just spoke about. And then what I'd like you to do is, once you've done numbers 1 and 2, for number 3, I want you to think back to what we talked about when we're setting one expression equal to another. And go ahead and go on Wolfram Alpha and actually graph these out, okay, and see if your solution makes sense. Okay? For your comment, I want you to make sure, of course, that you post a question or an answer. That's one part. And then the second part is that you actually post your solution that you found to number 3. So remember, those are two things: a question or an answer to someone else's question, and also your solution to number 3.